Good afternoon. Welcome to today's webinar. My name is Tracy Noble with ABB Power Systems, and I will be moderating today's event. Before we get started, I wanted to go over a few housekeeping items with you. All participant audio will be muted during the event today. If you would like to ask a question, please use the question chat box in the GoToWebinar control panel on the right side of your screen. We will answer as many questions as possible at the end of the event. Today's webinar is being recorded, and a link to the recording will be emailed to you following today's live event. Please feel free to forward this link on to people you know would benefit from the presentation. Today's webinar is brought to you by the Relion product family, Next Generation Protection and Control IEDs from ABB. So, just a little message from our legal department that ABB is pleased to provide you with the technical information regarding protective relays. The material included is not intended to be a complete presentation of all potential problems and solutions related to this topic. The content is generic and may not be applicable for circumstances or equipment at any specific facility. By participating in ABB's web-based protective relay school, you agree that ABB is providing this information to you on an informational basis only and makes no warranties, representations, or guarantees as to the efficacy or commercial utility of the information for any specific application or purpose. And ABB is not responsible for any action taken in reliance on the information contained herein. ABB consultants and service representatives are available to study specific operations and make recommendations on improving safety, efficiency, and profitability. Contact an ABB sales representative for further information. And today's webinar is Generator Protection Fundamentals with Mike Cockett. And Mike is a Senior Engineer Product Specialist for the Relion Family 670 and 650 product series. He is located in Raleigh, North Carolina. Mike has been a part of the North America SA Products team for 9 months. Prior to this, he worked as a Senior Application Specialist and Senior Regional Technical Manager for 12 years at the Substation Automation Product Factory in Västerås, Sweden. Prior to joining ABB in Sweden in 2000, Mike was Chief Consultant Protection Transmission at Eskom National Power Utility in South Africa. Mike joined Eskom as a training engineer in 1983. Mike graduated from the University of Cape Town with a BS in electrical engineering degree with honors in 1980. And it is my great pleasure to turn this over to Mike. Mike, take it away.
Well, thank you very much, Tracy. To all who have joined, good afternoon and welcome to this webinar. The learning objectives for this afternoon will be power generation fundamentals, generator faults, generator abnormal conditions, and typical generator protections. Now, the power station, as this slide shows, is the most complex part of the power system. In this slide, we can see the generator with turbine. Here we have the generator, circuit breaker, step-up transformer out into the HV system. We also have here the auxiliary transformer, excitation transformer, and a host of other things. This next slide possibly simplifies it a little bit more. It shows the power plant with the blue rectangle and then the HV substation with the red. So looking at the blue rectangle, once again we can see the generator with turbine, we can see the earthing system, we can see the excitation transformer with excitation system, generator breaker, the link off to auxiliary transformer, main power transformer, step-up transformer, then the HV circuit breaker and the HV network. Now, there can be, of course, a number of different equipment layouts in a power plant, and this would depend, of course, on the size of the generator. And if we look at the left there, you can see a single generator with or without the generator breaker connected to a unit transformer for connection to the network. In the middle, we have where more than one generator is connected to the same step-up transformer, and possibly these would then be for smaller generator sets. And then on the right, we have a picture which is typical for small hydro units. Now this picture shows the withstand capability of the stator core to ground fault currents. And if we study the curves here, we will see that it shows an area where there will be negligible burning, an area where there will be slight burning, and an area where severe damage can occur. Now, as you can see from this, the stator core can withstand very small ground currents, even for short duration. So to limit damage to the stator iron in case of ground fault, the max ground fault current must be limited to some small current, and here we typically look at about 10 amps primary. How is this done? Well, this is achieved by the grounding, and here you see a number of different alternatives for how this is achieved in practice. On the left, you get a star point that is solidly grounded through a resistor. This is reasonably typical, I believe, for Europe. Then next to it, we have a grounding transformer, and this, I believe, is more typical for the US, and then one or two other possibilities. Now, possible faults that we can get are stator earth faults, rotor earth faults, stator short circuits, stator or rotor interturn faults, unit transformer faults, and external faults. And through this presentation, we will be looking at each of them, and you will see what protection we can include in a generator protection system to cater for them. Then we also have a number of abnormal operating conditions, okay? And these, although they may not need to immediately trip the generator or the unit transformer, they need to do so. At some time, these conditions cannot continue. So if they do persist, then we would need to, at some stage, trip out the plant. Now this slide shows how the protection functions can be allocated based on what they safeguard. So if we look here, you will see that for the stator, for instance, there we are looking at things like the 87G or 87O, which is the differential protection, other protections like overvoltage, the overfluxing, stator overload, etc. Then you can look at the rotor, and there are a number of protections to safeguard that. We are talking about unbalance, which is the negative sequence protection, loss of excitation, pole slipping, etc. Now, if we take the negative sequence, for instance, the stator, of course, can handle negative sequence, but not the rotor. And then we have some protections to safeguard the turbine, and here we talk about reverse power or over and under frequency protections. Now, if you go to older protection equipment, then you can see that if you had a system with main 1, main 2, or A, B, then not all protection functions were duplicated. But today, with modern IEDs, if we are using a main 1, main 2, or A plus B system, then most protection functions can be duplicated, and this is really because of the multi-function capability of today's numerical IEDs. All right, so let's have a look then at what would constitute a generator protection scheme. So if you look at the slide, you will see that we have, of course, the 87G function, and this function then is connected to CTs on either side of the object, which in this case is the generator. But then we have a host of other current functions. So we would have overcurrent, we would have accidental energizing, there would be breaker fail, we would have thermal, negative sequence. And then, of course, we have a number of functions which would measure current and voltage. And here we are talking about things like the pole slip protection, under impedance, over or under power, loss of excitation. Then we have voltage measuring functions, and here we look at functions such as over excitation, over or under voltage, residual over voltage, and then also functions like over and under frequency. Then we have here for the rotor earth fault protection, you see we have showing the rotor earth fault protection using injection unit. Here we have the 95% stator earth fault protection using voltage based. We are also showing here the 100% stator earth fault protection based on third harmonic. And then there are also other functions that we would want to include for the metering or more measurements, I guess you could say. And there we'd be looking at measurement for display purposes of current, voltage, megawatts, megavars, etc. Then, of course, there may be other functions that would be required, maybe instantaneous overcurrent, maybe pole discrepancy, maybe voltage dependent overcurrent. And together, all of these functions would then make up your overall protection scheme to protect the generator. Now here we see really the same as what we saw on the previous slide, but now instead of having the 87G, the low impedance generator protection, we show the application using high impedance protection for the generator, and you can see it over here. So this, of course, requires dedicated and identical CT cores on both sides of the generator, and of course then you would design the high impedance circuit, and you would have to include also the external resistor and Metrosol. This once again shows really pretty much the same protection functionality as what we saw before, but now instead of using an 87G, the current is taken from the other side of the step-up transformer, and so now we get an 87O or overall differential function. Now the 87O function itself is pretty much an 87T really, because of the transformer that is now in zone, and so has to really handle all the same issues that a 87T function can handle. So then if we want to make a complete main 1 and main 2 protection scheme, we could do that with two identical IEDs, okay, each IED with an 87G, or of course it would be possible for smaller units really to have one IED with 87G and the other IED either with an 87T to protect then just the step-up transformer, or really with the same function but implemented as an 87O, which would then include both the generator and the transformer. All right, so let's expand then a little bit from what we had as the protection for just the generator. And here we can look at including optional protection for the step-up transformer. Now, if you look at this slide here, this bottom part is essentially what we had before, and this is the protection for the generator. It has the 87G. But now we can include protection for the step-up transformer, and here we would be looking at functions like the 87N, or restricted earth fault, 87T, okay, which is then the differential protection for the transformer, and it would have as its boundary this CT here, okay, these two CTs here, and in this case, although it's an 87T function, it's actually got the functionality of 87O in that it is including both the step-up transformer as well as the generator. Then if we have a look here, you'll see we have these auxiliary transformer or excitation transformer. Now, of course, these would have their own protection, but in this case, instead of including a second function or a second box for each one of those to act as backup in case the primary protection failed, it is actually possible to include those functions here. So taking this auxiliary transformer as an example, it would have, as I said, its protection, but instead of including the second function here, box here, to cater for the possible failure of that first box, this can be put back into this IED here. And here we see then a complete solution for the generator and transformer. Okay, to achieve such a solution as shown here would require 24 analog inputs. And this bottom part pretty much again indicates the protection for the generator. I just see I have a question here which I'll answer quickly. Somebody has asked what is an IED. Okay, IED stands for Intelligent Electronic Device, and today this is what we really refer, what we used to call relays. Today we call them IEDs or Intelligent Electronic Devices. Okay, so if we have a look here, this bottom part is pretty much the same protection of the generator. We have the 87G, and now we have the complete protection for the transformer, which includes the 87N or restricted earth fault. We have the 87T. So now this is not an 87O. It's actually 87T. So you can see it is measuring, the zone of measurement is the transformer. It is not including the generator. But then it's also possible to put in another 87O, okay, to give overall overall differential protection for the combined generator and transformer. And we can also have this overcurrent function that is the backup function for what is connected further down this buswork here. So this then is what an IED would look like, that has complete protection for the generator, the complete scheme of protection for both the generator and the unit transformer within the IED. All right, so now we've seen what functions can make up a protection scheme that is including then not only the generator but also the step-up transformer. So now we can start looking at some of the different faults that we can get. Remember that list a couple of slides back, and we can then look and see what protections will safeguard the generator or the unit transformer against these faults. So starting first of all then with a stator short circuit. Firstly, just briefly, consequences of stator short circuit would be that insulation, windings, and the stator core can be damaged. The large forces caused by the large fault currents can give damage to other components in the plant. There's risk of explosion and fire, and mechanical stress on the generator and turbine shafts. So if we look then at the what protection functions we have that can detect these stator short circuits, you will see, of course, there's the generator differential protection, there's the block or unit differential protection, okay, and if this is the 87O function, then as well as covering the generator, it will also include the unit transformer, but it may be a little bit less sensitive. The pickup sensitivity may be a little bit less than what we can set for the 87G. Directional negative sequence overcurrent protection, under impedance protection. We have the phase overcurrent protection, but this is really not so common because, you know, for current that is fed from the generator to the fault, this current will decrease over time, and we will have a look at that a little bit later. So what is maybe more common for current that is being fed from the generator is to have this voltage-dependent phase overcurrent protection, under voltage, and also the phase overcurrent protection of the block transformer. Now this is an overcurrent protection that is measuring current fed in from the system to the fault. So what we're going to do now when we're looking at the different fault types, always we're going to go back to our protection scheme, and we are going to look at what protection there is going to operate for the type of fault we are considering. So first up was this stator face-to-face fault, and there of course the primary or main protection function to cater for this is your 87G, okay? But there are others, reserve protection functions, and here we are looking, for instance, at the over here at the under impedance, okay? Here is phase overcurrent, and this is measuring current that is fed from the network. And then over here we have, if there is an 87O, then this will also cater for the fault within the face-to-face fault on the stator, but as I said, maybe with some slightly less sensitivity than the actual 87G. Now, looking at the 87G function itself, what is it made up of? Well, first of all, we have the unstabilized differential protection level. This is the high set level. The level, if the differential current goes above this level, then there's no doubt that the fault is internal. We have the stabilized differential protection level. Okay, this is your normal characteristic. And if we go into this operate area, it's not a direct permission to trip, but first of all we have to check with the blocking conditions to see whether a trip is permitted or whether we are in this operate area for some reason that is not actually a fault. Then we have the negative sequence unrestrained function. Now what this negative sequence function does is that basically it measures the negative sequence each side of the object, in this case the generator. It makes directional comparison based on direction of flow of these negative sequence currents on each side. And by doing this, it then determines whether this fault is basically inside or outside the protected zone. If it's inside the protected zone, then basically a pickup or operate from the normal characteristic can be translated directly into a trip without having to wait for the blocking functions to determine whether it in fact is a fault or not. So in this way we increase very much the speed of the operation. And then also it provides a negative sequence sensitive function, and this gives better sensitivity for detecting turn-to-turn faults than what can be achieved using just the basic differential protection characteristic. So this is then showing that. So here you see we have the unrestrained or high set threshold. Here we have the characteristic. It's in 3 sections. The ID min or minimum sensitivity here can generally be set for somewhere around about 10 to 20%. First slope starting here at about 100 to 125%, and second slope here at about 300%. Okay, and then the slopes for the first slope here around about 40%, and for the second slope around about 80%. And these values have shown to be good values for the differential function. So what should happen if the differential protection operates? Well, we need to close the turbine down. We need to take away the active power. We need to trip the generator breaker if it's available. We need to trip the field breaker. And if there's no generator breaker, of course, we then need to trip the HV side unit, HV side of the step-up transformer, the breaker there, and possibly also the fire protection. All right, this slide then just shows the layout really of what I've been talking about as 87G. All right, that's protection of the differential protection of the generator. 87T is differential protection of the step-up transformer, and then you have this 87O, which includes both the generator and the step-up transformer. But as I said to you, it's actually really an 87T function because it has to take care of the 87T capability as far as handling the transformer is concerned. So here we just have a look a little bit more then at this 87O function, or as I said, 87T. And you can see that it has pretty much the same characteristic as what we saw for the 87G. And really the only difference is maybe there's the need to set this ID min a little bit less sensitive than what can be set for the 87G. So we're talking about maybe somewhere around about the 30% mark. But as I said, otherwise it's really identical to an 87T, this which we are calling 87O, in that it has to handle the transformer, which means that it has to have the capability to do the zero sequence current elimination, to do the vector group compensation, and to do the transformer turns ratio compensation. Otherwise, it's pretty much the same as what we discussed for the 87G, in that, as you saw from the previous slide, there was an unstabilized or high set threshold. We have the normal characteristic, okay, and in order for an operate from that characteristic to be translated into a trip, we have to check that the blocking conditions permit this. And then we also have the same negative sequence function. So once again, if the fault is determined to be internal within the zone of protection by this negative sequence function, and we go above the characteristic, we don't have to wait for permission from the blocking signals, so we can trip much faster. And we also have the possibility of having the negative sequence sensitive differential protection, which gives better sensitivity for turn-to-turn faults than you would get from the normal protection characteristic. So if the 87O should operate, what should we do? So we should, of course, trip the turbine to close down the active power. We must trip the generator breaker if available, the field breaker, and the unit breaker. So now we go back to the picture showing the protection functions, and you can see here that if we had a fault, face-to-face fault in the transformer winding, then the main protection for this would be the 87O, okay, or of course the dedicated 87T if the scheme was implemented with this. But there would be other reserve protection functions that could see this fault, for instance the under-impedance protection here for feed from the generator side, and this phase overcurrent protection here for feed from the network side. Okay. Now, all we've done in this picture is we've moved the fault a little bit, so it's not actually now inside the transformer, but it's on the buswork. And actually, it's really the same protections that need to handle this. So it's still in the zone of the 87O as the main protection, or the under-impedance protection, or phase overcurrent protection for current fed from the network. Now here we've moved the fault along a little bit to outside the zone of the 87O, so you can see it's on the buswork beyond the CT that designates the boundary of the zone. Now, of course, there's probably some protection, the auxiliary transformer protection, that would essentially really be the primary protection for this fault. But as I mentioned earlier in the presentation, that if that is just a single protection, instead of including with that protection a second box to offer some backup, that backup can be relocated into the main generator protection IED, and so here you see that that is the overcurrent function now that would be the main protection, at least from the perspective of the generator IED, to see that fault. Okay. Also seeing that fault as reserve protection would be the under-impedance function, and or overcurrent function for current fed from the network. So here we just have a picture then that shows the different zones of protection for the different differential functions. So we have the 87G, okay, across the generator. So we would have CTs here and CTs here defining the zone of protection for this. Okay, then what is shown here is actually a separate 87T, okay, and the zone would be from this CT here to the CT down here to the CT over here. Of course, if this wasn't an 87T, but it was an 87O, as shown in most of the other slides, then this would not be the boundary CT, but the boundary would include down to here, and that would be the zone. And here we then have the zone for the differential protection for the auxiliary transformer. All right, so that finishes off then the differential protection. So we can look next at the under-impedance protection. Now, what is the purpose for this? Backup protection for internal short circuits in the generator or the unit transformer. Now this you have already seen in the slides that we've gone through, where there was the 87G or the 87O as the primary protection, but always as the reserve protection you saw that we had this under-impedance function. Backup or main protection for fault at the bus bar, where the plant is connected to the power system. So of course if it was intended as main protection, probably then the bus bar would not have bus bar protection. But if the bus bar did have bus bar protection, then it would be backup to that. Backup protection for line faults at lines out from the power plant. And then you could have a number of zones, okay, and you could then play with these zones with the reach settings and with the time delays you give them to get the protection that you want. So if you look at this picture here, which shows under-impedance protection with offset MO characteristic, and offset MO, really we're talking about, I guess, non-directional MO circle. And this is okay because we don't need, there's no need for reverse coordination, okay. And also we will only use the phase-to-phase elements of the, or the phase-to-phase, we'll measure only the phase-to-phase loops in the zones. And the reason for this, of course, is that we have the high impedance star point earthing, so we don't require, or we don't have need for the phase-to-ground loops. And in this slide is showing the use of two zones. Okay, zone 1 is covering the generator and the transformer, and zone 2 has a slightly longer reach and is reaching out to cover the bus bar and some portion of the lines out into the network. Turning now to the phase overcurrent protection, if you look at the bullet points here, you'll see they are very similar to what was said for the under-impedance. Okay, so we're talking about backup protection for internal short circuits in the generator or unit transformer, and that we saw, and primarily though for current fed from the network side. Backup or main protection for fault at the bus bar where the plant is connected to the power system, and also backup protection for line faults at lines out from the power plant. Now, one thing to bear in mind when we are considering overcurrent protection, that measures current that is supplied by the generator is that the fault current from the generator will actually change during the fault sequence. And here are some reasons for this. Firstly, it's due to the change of generator reactance that will change from XD double prime to XD prime and then to XD. Now if we look at XD double prime, this reactance value is somewhere around about 20–30% to XD, which can be somewhere around about 200%. And then also if we look, it's dependent on the type of excitation system. If this is such that a low voltage, which of course will be there due to the fault, can cause reduced field current. So then what we do is we look at what is termed voltage dependent phase overcurrent protection. And if you look at the characteristic, okay, here we have, this is probably around about the 1 per unit voltage, where you would have the set threshold such that for maximum load current that can be produced by the generator, this threshold would then be above that. But for reduced voltage, then the actual pickup threshold would reduce, and typical values for this point here is about 25% of the set value for here, and this point here is about 0.25 per unit as well. So let's look at what happens then if we have a short circuit that is fed by generator current from the generator. Now before the fault, we would be sitting here at the 1 per unit voltage point, okay, and you can see for 1 per unit voltage, the load current would be with good margin below the pickup threshold of the overcurrent function. But then what happens, the fault occurs, and initially we have reasonably high fault current. The voltage, of course, will decrease, and so the fault current would be easily above the threshold. But of course, this is not an instantaneous trip. Okay, we are wanting to trip after some time delay. It's some backup function. And if you look at this, then after about 400 milliseconds, if that's the trip time, then we would have now, because of the factors I spoke about earlier, we would have now fallen below the pickup threshold if this was constant. So it's for this reason that we have this voltage controlled overcurrent, for overcurrent that is fed from the generator, such that for low voltage, or for then we have this decrease in the pickup threshold, and then you can see that after the time delay, should it be necessary that this protection function should now operate because something else has failed to do so, then it would still be above the threshold. So now this has a slope. It's also possible to have voltage controlled phase overcurrent where you have a step. Okay, I won't really discuss this much more, but it's also possible to implement such a function. So let's have a look then. If we have this external face-to-face fault, now for this external face-to-face fault, we are going to be supplying current from the generator. So it's outside the zone of any of the differential protections. So what do we have then to see this? Of course, is the underimpedance, okay, and the overcurrent, phase overcurrent. But remember, if that is pure phase overcurrent and not voltage dependent, it may not really be able to do the job after the required time delay. So this is for an external phase-to-phase fault. If we have an external earth fault, okay, then of course we have the protection here, the ground fault overcurrent here, measured in the star point, okay. We also have the underimpedance, and then depending on the level of the actual phase current for that fault, we have also the phase overcurrent. But all really as reserve protection functions, because primarily for the external fault we would expect to have some busbar protection, or if the fault was close in on the adjacent lines, we would expect to have the primary protection on those objects to clear this fault. All right, let's have a look now at the stator earth fault. Now, you remember from very close to the beginning of the presentation, we spoke about possible damages to the stator iron, and hence the need to limit the stator earth fault to a reasonable small value, from around about 10 amps primary. Because of this high resistance earthing, when we do get the stator earth fault, we have the we get the increased voltage on the healthy phases, small fault currents. Because of the small fault currents, we have a reasonable high sensitivity requirement, okay, for the fault detection. The fault resistance is normally low at stator earth fault, okay, because the fault, I guess, is to the core. And then the residual voltage and the earth fault current is highly dependent on the fault location in the generator, and that you will see from these next pictures. Now, here they're showing measuring the stator earth fault voltage based, and if the fault were here on the terminal, okay, then in primary value, the value of U0, V0 primary would be given by this, okay. But should the location of this fault move down the winding towards the start point, then the value of U0 would become less and less and less. And so that means if you are going to detect this fault with a U0 over voltage function, there will be some area around the start point where the measured U0 will not be above the threshold. And a similar argument for current-based stator earth fault protection. So once again, if you had the earth fault right at the start point, there would be no 3R0, and if the location of this fault should then move along the winding, you would get more and more 3R0 to measure. And once again, if you had a protection based on going above a threshold, you would have to move, the fault would have to be some small distance from the start point before the current would go above that threshold. And that's why we talk about 95% stator ground fault, okay, because whether we're using the voltage-based or we're using the current-based, we can't get to really the last 5% just before the star point. Okay. But of course, this is not, we need to make a plan how to get around this. And there are two ways of really of achieving the 100% state-to-earth fault protection. Okay, the one is the third harmonic principle. Okay, and this is based on measurement of the natural third harmonic voltage induced in the generator. And the second one is the injection principle. Now, if you look at the third harmonic principle, you could say the plus here is the price. Okay, it would not cost really any extra money. But the minus here is that this method cannot detect an earth fault inside the stator when the machine is at standstill. And the other thing to bear in mind is that the effectiveness of this third harmonic method really depends on the type of generator, because the amount of third harmonic voltage induced in the generator is type dependent. Generally on hydro units it can be quite okay, but on thermal units maybe one would have to investigate a bit. If we look then at the injection principle, the minus here of course would be price. Okay, you need to add also the injection equipment. But the plus here is that with this method you can detect a stator ground fault even with the machine at standstill. So, as I said in the last slide, the third harmonic voltage is generated by the generator itself. It has the characteristic of a zero sequence component because it has the same phase angle in all three phases. The distribution of the third harmonic voltage depends on a number of things. It depends on the neutral point grounding method. It depends on the stator winding capacitance to ground. It depends here on the generator CB capacitance to ground. Not shown in the picture, but it depends also on the generator transformer low voltage delta winding capacitance to ground. Now you can see that whether or not there's a generator breaker then can make some difference. If there's no generator breaker, then this capacitive coupling doesn't change, okay, because it's not possible for that point to be open. But if the generator circuit breaker is there, then the capacitive coupling differs between operating conditions. Now, mostly it would be closed under all normal operating conditions, but during standstill or during run-up, then it would be open. Now, the simplest approach for using the third harmonic would be just to use a third harmonic under voltage for the third harmonic voltage measured in the neutral, or a third harmonic over voltage for third harmonic measured at the generator terminals. And the reason for this is because if you have the earth fault near the star point, then the third harmonic measured at the neutral side, at the star point side, would go below a threshold, or the third harmonic measured at the terminal would go above a threshold. It would increase above the threshold. But these two methods have some problems. For instance, during generator startup or generator shutdown, okay, you would need to block them. So the best method to use then, if you're using the third harmonic, is to use the third harmonic differential principle, in which you calculate an operate quantity and a restrain quantity. Now, I don't want to go into that in too much detail right now, but what's important, if you just have a look at this picture, you see then the whole stator winding here. Okay, now remember what we said previously, that using the fundamental frequency, either voltage-based or current-based detection of stator ground faults, it was not possible to see the last 5 or 10%, depending on the threshold of the pickup, right at the start point. Now, this third harmonic-based differential function, that is where it is operating, and it covers really only roughly the bottom, somewhere around 20–30% of the winding. So there you see you have the one fundamental frequency protection is covering from about the 10% mark up, and the third harmonic differential is covering from the 0 to about 30%, and by using these two together, we then achieve the 100% stator earth fault. Now, that's the third harmonic principle. It is also possible, as I said, to use the injection, and here you would need, of course, then to get the injection unit, and you would need to couple this injection unit to the point, this is at the neutral point where you would connect it to the stator, and you would also then, of course, need to connect it to the IED. So the IED would then, based on the quantities it receives, then make a determination whether the stator has a ground fault or not. So looking at this then, going back to our picture, you see that if we have a fault in the earth fault in the stator, now this particular earth fault is not meant to be at the start point, and then you can see that that we have the 95% function in this instance, the voltage-based one, that would detect this fault as the main protection, and then as reserve protection, we would either have the injection unit, if it were there, or we would also have on the terminal side measurement of residual overvoltage. Okay, now we have the earth fault close to the start point. Okay, and here you can see really there's no other reserve protection in the IED. So really the only things that we can have to cater for the fault here is really to have the third harmonic 100% function, or the injection function. Now here this slide is showing both of them, but I guess it is not necessary that both have to be applied in any one installation. All right, if we look then at earth fault in the transformer HV winding, okay, here of course we have the, if it's on the star winding, okay, we have the 87N, or the restricted earth fault, as the main protection. As reserve protections would be the earth fault or ground current measurement in the star point. We have also the under impedance function, and we have the overcurrent, phase overcurrent function should the current in the faulted phase be such that, fed from the network, that this can be detected then by this overcurrent protection. If we have a fault in the transformer LV winding, now this is the delta winding, okay, and here then really the main protection for this would be a residual overvoltage function, but it would also be able to be seen by the earth fault, the overvoltage earth fault protection on the star point, okay, And if you were using the injection principle, it would also, this injection would also be able to see this. Okay, this is just moving the earth fault then a little bit down the buswork. Okay, so now we are, I'm just trying to see, okay, and the main protection here, of course, then would be the residual overvoltage protection. Okay, and once again, it would be possible to be seen by the overvoltage protection on the earthing resistor in the star point, and also the injection function could see it. Now, turn-to-turn fault in the stator winding. Traditionally, the 87G, okay, may not be able to see this. Okay, so one scenario, of course, is to wait. Okay, nothing will happen, and if this fault then should develop into an earth fault, okay, then you have those functions which we discussed already, which would be able to detect it as an earth fault on the stator winding. But what is perhaps not shown on the slide is, and remember I was speaking about this negative sequence function that is now, and in particular the negative sequence sensitive function that forms part now of our of the 87G function, and this function then offers better possibility, more sensitivity to detect such turn-to-turn faults than what you can get from the traditional 87G function or phase function. Okay, another possibility, of course, for detecting turn-to-turn faults is if you have the split stator winding. Okay, one option, of course, is then to look at the unbalance that you would get here in the star point from the two windings. And another possibility, of course, is to make a differential function between, okay, the current flowing in the two windings. To do that, of course, you would have to, of course, bring these CTs in separately. And by measuring them separately, you could then, oh, sorry, it's this one here, and over here, and you could then make a differential between these two currents. And then, of course, you could still have your normal 87G, okay, but now from the neutral side of the generator, we would just need to measure both those currents. And then, of course, we could sum them because the other protections are not really interested in how the current is split in the stator, and so we would sum them, and the summed value would be fed then to the other functions. Right, rotor earth fault. So the field circuit of the generator is normally isolated from earth. When a single earth fault in the rotor, with a single earth fault in the rotor circuit, is it possible to have continuous operation? Okay, because the rotor is normally isolated from earth. But of course, the problem is what happens if we should get a second one, and then you could have large current and risk of severe damage. So the requirement for fast clearance, you could say, is moderate. Just because we have one doesn't mean the next one would come, I guess, immediately, but it's something that you would not want to ignore. And here we have then the injection principle. So once again, you would need the injection unit. Okay, but now instead of using the injection for the stator, we would use the injection for the rotor, and we would connect this then to the rotor, and as feed also the quantities to the IED, so the IED would then make the right interpretation of or be able to make interpretation of the injected quantities and to decide whether the rotor had an earth fault or not. So this is just showing the picture there where now you have the rotor earth fault, and so the main protection function within the IED would be this function for the rotor injection, but of course you would need to have the external hardware as well to make the injection. Now if you had a turn-to-turn fault in the rotor winding, well, you could say that this would be detected when this develops into an earth fault. So there's really nothing that is detecting this, okay, until it becomes an earth fault. So this is shown in blue here. But should this turn-to-turn fault develop into an earth fault, then this injection principle would be able to handle it and detect it. All right, looking quickly then just at the machine itself, because now we want to start looking at some of the other issues. So I think all of you would agree that a synchronous machine can supply active power. Okay, then it operates as a generator. If it receives active power, it's a motor. It can supply reactive power, okay, in which case it's an overexcited machine, operates as a shunt capacitor, and it can receive reactive power from the system, and then it's an underexcited machine, and it operates as a shunt reactor. Now, when we're looking at some of these other protection types, it's useful to look at different planes, okay. You can see we have what we call the UI plane, okay. We have the XR plane, and we have also the PQ plane. And the PQ plane is the plane which we are used to seeing then the generator capability diagram. Okay, loss of or under excitation, okay, there are a number of causes for this. And the consequences, of course, is that the machine speed can be then higher than synchronous speed. This is for a generator. If it was a motor, it would be the opposite. And really the reason for this is that we require the rotor current to get the coupling. Okay, so what you could say then is we have this asynchronous running of a synchronous machine without excitation. Okay, and you can get stator and core heating, you can get induced rotor currents, and this is what would be the consequence of this. Okay, this slide just shows what the measured RMS values of voltage and current would look like at loss of field. And if we view that in the S-plane, it looks a little bit like this. So what protection do we apply? Well, generally we have these two zones of underimpedance, offset MO, and also this directional line. Okay, and the main purpose of this directional line is really to create or to achieve additional stability, because it will be a restrained area. Now, one thing just to bear in mind is that if we look back at this slide, okay, which was drawn in the PQ plane, okay, and you can see where the locus is, and we look at this picture that looks like, of course, that we have the underimpedance protection in exactly the right place. But just remember that this is shown in the XR plane, and if we want to convert from the S to the Z plane, really it's only valid for fixed voltage, and of course in circumstances of loss of excitation, then the voltage is not constant. Okay, but nevertheless, I guess over years experience, this has been shown to be the best protection to handle such loss of excitation. And if we look at, once again, our protection, we'll see there as the main function the loss of excitation function. And if you remember from a slide or two back, the current increased, the voltage decreased some. So as reserve functions, maybe we could get operation from either an overcurrent or a undervoltage protection. Generator motoring. Now, as we all know, that a generator should produce active power. If it starts to receive active power, it then would act as a motor. And although this is not a problem for the generator itself, it could be rather dangerous for the turbine. So here we have the causes, we have the effects, but the important thing to look at is the demands on the measurement, because we need to measure the active power very, very close to sort of the zero mark, but actually the Q could be quite high. Now, this is showing an overpower function and an underpower function, and in each case you can see you have a magnitude to set and you have an angle to set. So the overpower function is for powers above the magnitude, and for underpower it's below the magnitude set, but you also have to take or bear in mind the angle. So the easiest way to visualize how these would operate is if you take the overpower one, for instance, and take that angle and spin it around 360 degrees, and that would basically give you the operate area for any set angle, and similarly for the underpower case. So one way then of detecting then that this we're not producing active power is to have this reverse power protection. Now, if you think of this here, this would be an over power protection, but with this swung around, so this angle is 180 degrees. And in this case, this would give you the operate line here. So the operate area would be this side, and this would be set with some margin, because here would be the operating point of what would be the power into the generator without the operating point without the turbine torque. So that would be the reverse power protection, would be really an overpower protection, but it's also possible to have low forward power. Okay, now this would be an underpower protection if we look at this one over here, but with the angle such that this is in this direction, and so this would be an underpower protection with the operating point to the left of the line, and then, or the pickup would be to the left of the line, and you can see the operating point for the generator operating without the turbine would be where that black dot is. And here we have that protection in the in our protection scheme. So here is the overpower protection, but of course then as reserve we would have the underpower. Negative sequence overcurrent. So here from the asymmetric currents, okay, we can filter out the negative sequence. So here if we have asymmetric currents, then of course we can calculate negative sequence. Now, why is negative sequence hazardous to the rotor? It's hazardous to the rotor because it rotates in the opposite direction. So it induces 100 hertz, or I guess 120 hertz in the 60 hertz system, current component into the rotor, and as a consequence the rotor ends can overheat. So this is normally describing the capability of the generator to negative sequence. And what this K generally represents is for how long can the generator withstand 1 per unit negative sequence current. Okay, and from that you can then create the characteristic to ensure that you have the right tripping time. So I won't go through all of this. We have the causes for such negative sequence, and as I said, the characteristic, that K value is something that would be provided by the generator manufacturer, and as I said, what it means is it would be some seconds or some number of seconds, and what it means is that's the number of seconds that the generator can withstand 1 per unit negative sequence current. Okay, and there you see here we have the negative sequence function here. Okay, this is the same thing, but okay, here we have a broken stator winding, and here we have a broken transformer winding. But in each circumstance, the protection that would see it would be the negative sequence function. Pole slip or out-of-step protection. Now remember, with the loss of excitation, we had the asynchronous running of a synchronous machine without excitation intact, but if we are talking about pole slip or out of step, then we have asynchronous running with excitation intact. Okay, so it's characterized by power oscillation, P and Q. Okay, manifests as impedance movement in the R and X plane. Okay, it has big mechanical impact on the turbine and shaft. It's typically caused by, well, there's some things like long fault clearance times, inadvertent tripping of transmission lines, etc. And here again, if you look at the protection picture, you'll see where we have the pole slip protection, and as a reserve function, maybe also we could have the loss of excitation. Then we have over and under frequency. Okay, and here is a where we have the under frequency in the in our protection. Now, one thing to bear in mind, of course, is for the turbine. I mean, the turbine is really rated to operate within quite a narrow frequency band. Okay, so one of the protected objects, of course, here would be the turbine. Also the transformer, because we will talk a little bit later about the overfluxing. Okay, and then, of course, if we have overfrequency, this picture here shows where we have the overfrequency protection. Over voltage protection or over voltages, this can come, of course, from faulty AVR. It can come from a sharp increase in the voltage because of load rejection followed by some machine runaway. And so you can see in this picture we have the over voltage protection, that's phase over voltage. And also as a reserve function we have the over excitation, because this is also working on there being an over voltage. So we look at that now, this overfluxing or over excitation. Okay, and you can see that then the flux or the induced field is proportional to E, which is the induced EMF divided by the frequency. And of course we are not measuring E, so we can measure the terminal voltage. So this is very nearly equal to, also proportional to U divided by F. So you can see that the flux or the induced field will increase for over voltage or increase for under frequency. And okay, I don't intend to go into this function anymore here, but other than just to point out that, of course, we have the over-excitation protection in our protection package, and also here we could possibly measure under frequency, and it's not really shown, but possibly we would also be measuring over voltage as reserve protection. Thermal protection, okay, thermal overload. All right, I don't want to go too much into this really, but this picture is just showing that, you know, we have some, it would be a thermal function. It's not really just overcurrent function, it's a thermal function. It has time constant. It operates on really on heat buildup in the object. And here you can see, although the measurement is really based on current, but the algorithm is based on heat buildup in the transformer or generator. Rotor thermal overload. Okay, this is really based on here measuring current. There is some ANSI or IEEE equation for this. But if you look at this equation, it's really more of just an overcurrent type of protection rather than true thermal protection. We have accidental energizing, okay, which operates when the generator is at standstill and is then energized by mistake. So here also in our protection package, we have the this function for the accidental energizing. Breaker fail protection. This, of course, is protection that will be informed that a trip has been sent to the circuit breaker, and then it will determine whether the circuit breaker in fact opened or not. It can make this determination by seeing that the current reset, or if as well as the current, you can use contact, and it would see that the breaker opened by monitoring that the auxiliary contact change state from closed to open position. It's possible to get re-trip functionality. The backup or bus trip, okay, there's actually, you know, the trip comes after the normal T2, but depending on the number of breakers that actually have to be tripped, and maybe this is not applicable for power plant, but depending on the number of breakers that are actually tripped by the protection, if that's a large number, then maybe you want to trip them in batches, and so you have the option of the first batch being tripped after T2, and then starting from T2, there's a T3 timer that would trip the remainder. So here you can see we have the overcurrent protection, and there are two of them, one for the generator breaker, one for the breaker on the HV side of the transformer, and each of them would get initiated or started by protection that is tripping the breaker that they are assigned to. And then finally, we can look at this destroyed bearing insulation. Okay, if you look at the picture, you can see that we have the bearing insulation, and this protection is really designed around this special shaft current transformer. Okay, and should the bearing damage such that we get current flowing then in the shaft, this can be detected, and because we can actually get damage to the bearings if this current exceeds about 1 amp. So okay, to conclude then, this is the same slide that we saw many slides ago. I said we would look at all the different types of protections the state-to-earth faults, rotor-earth faults, state-to-short circuits, state-to-rotor, interturn fault, external faults, and all the abnormal operating conditions. And we would go through them, and we would see what protection we had in our generator protection package to handle these. So, okay, thank you very much. Now I've come to the end of the presentation. If you just give me a few moments, I will try to see what further questions I may have. I just need to. I don't know how to make this bigger. Okay, let's have a look. Okay. How can I make this bigger? Oh, there. Okay, cool. Oh, okay. All right, I'm just going to look down and see what questions I can see here. Okay, and okay, I can see with the 87O, we consider auxiliary transformers HV side, why not LV side also? Well, we don't really consider the HV side. If you, you know, the zone for the 87O would, I mean, stop at the CT location, and from that CT location, I guess you would get the zone for the auxiliary transformer. So I think it would be a little bit difficult to include the whole thing in the 87O because you probably have two different transformer vector groups and that, and maybe it would be very difficult to balance the thing properly. Okay, where am I going now? Okay, there's a question about cyber attacks, but I think this is something that we can handle outside the questions here. I would certainly, if somebody, the person who sent this could send me an email, I think I could give him the information of where we stand on that at the moment.
Mike, excuse me, this is Tracy. Just so everyone knows, there are a number of questions. The question box is full, and we are running short on time. So if, Mike, you can find a couple of questions that you think you can answer in the next 5 minutes or so. If you do have a question in here, we have that and can respond to you by email, and we do have your email address as that was required when you registered. So whatever we don't answer here, we will respond by email to you. Mike will actually reply back to you because he's got a slew of questions. So
Yeah.
sorry for the interruption, Mike. Go ahead.
No problem, no problem. Okay, somebody asked about the minimum differential pickup setting for 87G and 87T. I think I may have answered that one after the question was posed, but for 87G, we are talking, I guess, somewhere around 10 to 20%, whereas for the 87T, we need to maybe look around about the 30% mark. Of course, it depends on a number of things. If you have a tap changer, okay, then you're not compensating, you're not bringing in the tap position information, so you can compensate in the differential calculation for the tap position. Then, of course, you have to bear the extremes of the tap position in mind when you set the minimum sensitivity. If you are bringing in tap position, then maybe you could go a little bit more sensitive, of course, than if you're not. Okay, what is the basis to arrive generator unstabilized differential protection setting? Okay, here you just have to be absolutely sure that if you go above this threshold, that the fault is definitely an internal fault. There can be no other reason, no other reason that can take you above this this threshold other than you have the internal fault. So I guess to some extent you need to know your fault levels, and you need to know what maybe is the worst case scenario, maximum differential current you may be able to measure for a non-internal fault, or for a fault where you would want blocking to come in and ensure you don't trip against being sure that the fault is internal. Because if you go above this high set threshold, then that's immediate permission to trip. Okay, on what basis we decide N section 1, N section 2? Are they fixed for all generator protection? No, they're not fixed. Well, I can talk really just about ABB, but in ABB, the N section 1 and N section 2 are settable, they're not fixed. The N section 1, normally we are looking somewhere around about 125%, which means you maintain the flatline stability for 100% load, maybe a little bit of overload, particularly if you're talking about transformers. For these conditions, really, or for this area, really, what can cause differential current, of course, is non-compensation for tap position, maybe some over-excitation or something like that. But as far as the CTs are concerned, I think you're relatively in a good area for the CTs. Then the next zone, section 2, where you have the first slope, the recommendation there is to go up to about from the 125% to 300% mark. And here, if you look at CT characteristics, up until about the 300% mark, at least if you're talking just about current magnitude, not DC offset or something like that, but if you're talking just current magnitude, CTs can normally replicate that rather well. And then for currents above the 300% mark, then you can start getting, I think, more problems with the CTs. more saturation can start occurring, and then you would want to increase the slope.
Okay. Hi, everybody. We're going to wrap it up because there's still a lot of questions. And as I said, Mike can respond to these through email and get the information that you're looking for. But we are almost 8 minutes over, and I know all of you need to get back to work. So